All right. Fun stuff today. Hey, Major told me one of the homework problems got really nasty. Which one is it? And I'll see if it's a fair amount of nasty or if it's one I want to. Yikes! Holy cow! Oh man!
I'm sure you.
And Izzy wrote, "This made me cry" at the bottom. I'm so sorry. It's never my intention to make anyone cry.
I did 65 last night, and then it was like 1 a.m. when I finished. Like, I'm too tired for this.
Okay.
I finished my homework last night.
Okay. Bless your heart. I will take a look at that and possibly omit it from any future assignment, Sam, if I get to teach Cal2 again someday. Yeah, I'm going to make a note, maybe not to assign that problem, because it's not my intent to make anyone cry. Although, Cal2 did make me cry, but it was my teacher, I think, more than Cal2. If I could have had Carlos Spake for all of my calculus, then I might have been an engineer. No, I wouldn't have. I'm not good at that. All right, 5.6. Let me do a little drawing talk here for a minute. You know, drawing's not my strong point, but so far we have been talking about finding the area under a curve, and we started by using rectangles to do that. And we said if you choose certain rectangles, you'll get an area that's too big. If you use certain rectangles, you'll get an area that's too small. The mean value theorem guarantees us that there is a rectangle such that the area of the rectangle will equal the area that you're looking for. So there is a perfect size rectangle. And then we stopped really using rectangles once we found out that the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit will give us that same value without having to use all those rectangles and that limit formula for finding area. Well, somewhere, I don't know what was going on in his or her life that made him think of this, but somebody said, you know, instead of using rectangles, this would be a little bit better approximation if instead of rectangles, I used trapezoids. How about that? I can see that that would be better. Looks like trapezoids fit that better than rectangles did. So let me figure out a way to use trapezoids to estimate the area under that curve rather than using rectangles. And William's so excited, he's just grinning like a Cheshire cat over there. Like, oh yes, trapezoids, I love them. How do you find the area of a trapezoid? It's almost a rectangle, except for it has a short side and a long side. What?
Something about base 1 and base 2.
You average the short side and the long side, and then multiply times the width, and that's it. You multiply the width times the average of the short side and the long side. So that's how you find the area of a trapezoid. And then, of course, somebody said, let's find the area of infinitely many trapezoids. The only way that this could get any more fun is if I found this limit as the number of trapezoids goes to infinity of the sum of the area of infinitely many trapezoids. Yeah, this was way before video games were invented, or it never would have been invented. Let me show you a little bit of math that I don't want to do. It would be like doing number 65 again. This is the book, and shows you, here's a bunch of trapezoids on an interval from A to B, and the area of any, well, each trapezoid, right here's what I'm trying to highlight. Each trapezoid has the width of the length of the interval divided by the number of trapezoids. So B minus A divided by N would give you the width of each trapezoid. And then the area of each trapezoid would be, this is f of x1 or f of x0 plus f of x1 divided by 2. That's the average of the height of the short side and the height of the tall side. And then multiplied by the width of the trapezoid. So this is how you find the area of one of those trapezoids. And if we put a limit on it and we started adding up the area of a whole bunch of trapezoids, then we would find out that, hey, sure enough, that gives us the same thing as the definite integral. It gives us the area that we're looking for. So we're using 2 rules today to find pretty good approximates, but approximations of area under a curve for functions for which we cannot find the antiderivative. Now, the second fundamental theorem of calculus guaranteed that every function over any interval over which a function is continuous, that function has a antiderivative. Second fundamental theorem of calculus guaranteed us that, but it very cleverly didn't guarantee us we could find it. See the difference? It guaranteed there was one. It didn't guarantee we could find it. Some functions like square root of x cosine x, cube root of x, square root of 1 minus x, square root sine of x squared, you can't squint hard enough to figure out those antiderivatives. And U substitution won't work to find those antiderivatives. Some functions don't have antiderivatives that are very easy to find, but we can still find the area under the curve by using numerical integration rather than finding the antiderivative. And there are 2 rules in this section, the trapezoidal rule and Simpson's rule. I think the guy who invented the trapezoidal rule should have named it after himself like Simpson did, but he didn't. Just call it the trapezoidal rule. And you will see it at the top of the next page. Let f be continuous on an interval from a to b. That's what guarantees that there is an antiderivative in a definite integral from a to b. On the right-hand side of that equation, it tells us how to find it if we can't find the antiderivative. Now, there was a whole lot of algebra on the previous page leading up to this, but you can still kind of see this is finding heights of trapezoids multiplied by the width of a trapezoid for infinitely many trapezoids. All right, I don't want to do all that algebra on the previous page on the board. It's cool, you can look at it, but I don't want to do it. I just want to be able to use this. And to use this and distinguish it between the trapezoidal rule and the Simpson rule to know which one you're using, notice that in the trapezoidal rule, the coefficients of these heights of rectangles are, the first one's 1, the last one's 1, every trapezoid in between, or every height in between the first one and the last one, the coefficient's 2. So you're just going to remember for the trapezoidal rule, I need to add up the heights. Oops, switch back to this. This is adding up the heights of a whole lot of trapezoids, and the coefficient of the first one's 1, coefficient of the last one's 1, all the coefficients in the middle are 2, and then multiply that by the length of the interval divided by 2n. So if this is on the test, and this is on the test, here's what I'm really remembering. Here's what I really have to remember about the trapezoidal rule. This first coefficient, and then that's what I'm really going to remember for the trapezoid rule. Now, it's a formula. It's a recipe. You give me a recipe, I can use it. All right, so let's see if we can use that recipe on this number 10. Let's try to find the area under that curve from 0 to 2 using, let's use 4 rectangles. In the homework, it says use 4 rectangles. The more trapezoids. The more trapezoids we use, the better approximation we would get. So we could do this using 8 rectangles or 12 rectangles or 100 rectangles. And every one of those would be a better approximation than the one before, but it would get so painful that nobody but a calculator or nobody but a computer would actually find that area that way. On a computer, you could iterate that 100 times really quickly. Without a computer, it's not going to quite be as bad as 65 was last night, but it's still going to take a little bit of work. So number 10 on page 344. We want to find the area from 0 to 2 of x times the square root of x squared plus 1 dx using 4 trapezoids. And using the trapezoidal rule, we'll also do this by Simpson's rule in a minute, but first we're going to do the trapezoidal rule. You know what? If you just gave me that problem on the test and said find the area, then the first thing I would probably try to do is one of the methods that I know. Could you use substitution on that? Does that look like something you could use substitution? Yeah. The first 2 problems in the homework, you're going to do multiple things, but the first 2 problems in the homework, you're going to actually use the trapezoid rule, then use Simpson's rule, and then use substitution to show that those 2 work, and you do get a very close approximation to what substitution gives you. Now, unless you told me I had to, I wouldn't do this by trapezoidal rule or Simpson rule. I would, since substitution would work, I'd use it. But the last 2 problems in the homework, your use substitution is not going to work. That's when you would have to use the trapezoidal rule or Simpson's rule. We're just kind of proving it works right now. So the trapezoidal rule says that antiderivative or actually that definite integral, it's not an antiderivative, it's definite integral, equals b minus a. What are a and b here? All right, a is the lower limit and b is the upper limit. And so b minus a over 2 times the number of trapezoids, and we're told to use 4 trapezoids. Now let's look at this recipe again. B minus a over 2n, I have that. What's this f of x sub 0, 2 times f of x plus 1? What's f of x plus 0? What does that mean? You start with the 0 and you work your way up to the 2. But to know what to count by, you have to use the width of a trapezoid. The width of each trapezoid, and I'm just going to go back and put that right here. The width of each trapezoid is delta x. And delta x is just the right endpoint minus the left endpoint, the length of the interval, divided by the number of trapezoids. And actually, I had that right here and I pointed at it in the book, but I didn't make a big deal of it while I was pointing it at it. That's how you find what you count by. So we're going to count by a half. So that means our first x value is going to be 0. And if we're counting by halves, what's the next one going to be? A half. And the next one's going to be a whole. And the next one's going to be 1.5. And the last one is going to be 2. So that breaks our whole interval up to 4 partitions. 4 partitions would have 5 fence posts, but that breaks our whole interval up into 4 positions. So we want to multiply this b minus a over 2n times f of our first x plus, remember all the other coefficients are 2. So 2 times f of our next x plus 2 times f of our next x plus 2 times f of our next x. And now that we're up to our last x, that coefficient is back to 1. 1 times f of 2. So it's cumbersome. It's not difficult, but it's cumbersome. We've still got a way to go here. First, identify your width of the interval, which we found to be a half. Start with your left endpoint and find all your other x's by adding a half. And then plug it all into the recipe. F of 0 is just what you get when you plug 0 into the function. And this leading coefficient, this coefficient 2/8, I'm going to go ahead and reduce it to a 1/4. What do you get when you put 0 into the function?
0.
Yeah, 0 times square root of 1 is 0. Plus 2 times whatever you get when you put a half into the function. Do as much as you can in your head. When you cease to be able to do it in your head, write it down. If you put a half in place of both x's, you'd have a half times the square root of a half squared plus 1. This is this. This is this. The third term is 2 times f of 1. That's 1 times the square root of 1 squared plus 1. That's the third term. The fourth term is 2 times 3/2 put into the function would give you 3/2 square root of 3/2 squared plus 1. And the fifth term is 1 times 2 put into the function. 2 put into the function is 2 times the square root of 2 squared plus 1. Now, notice in the homework, I've taught you very specific instructions I said, use the trapezoidal rule to approximate the value of the definite integral, and then use Simpson's rule to evaluate the, approximate the value of the integral. And then find the exact value on the first two problems, because you actually can. You can use substitution, and then check all three of them on your calculator. Make sure that all three of those are darn close to what your calculator would give you there. So we want to clean this up as much as possible, and then we can get a 4 decimal approximation of it. I'm not going to talk all the way through cleaning that up. Let's just all go for it and see if we end up with the same thing. Scares me how quickly y'all reach for a calculator. You should at least get that far before you pick up a calculator. For some reason, I rounded to 3 decimals instead of what I said to do, which was 4 decimals. I got 3.45. What are the next two? 6, 7. All right. William, what is it? You were just always screaming. Was it fun or just what?
Oh, the answer is 3, 4, 5, 6, 7.
Oh, okay. I didn't even get that. Chase doesn't think it's as funny as William did. All right. Again, this one we could have found the exact value by substitution, and we're going to do that in a minute. But when we do, we're going to get something darn close to 3.4567 and find out that trapezoidal rule worked pretty well. All right, any questions? Just a recipe. A little bit of an ugly recipe, but it's a recipe. And then somebody, well, I know this somebody's name. This somebody's named Simpson. Simpson was even more clever than Mr. Trapezoid.
But his name was Trapezoid. That's
I know, that'd be awesome.
Maybe his name's Trapezoid.
I bet trapezoids were around a long time before the trapezoidal word.
Yes, but his name had been Trapezoidal.
And then retroactively, let's just call them trapezoids. Okay, so we began finding area under a curve using rectangles. That must have been Mr. Rectangle. And then Mr. Trapezoid said, you know, trapezoids would give us a better approximation of that. And then Simpson said, I can do even better than that. Instead of trapezoids or rectangles, what if we used kind of what is still rather geometric, well, not, that doesn't make sense, not still geometric, but still has straight edges there. But instead of connecting these 2 points with a straight line, what if we used a parabola there? A parabola is darn close to what that's actually doing. What if we use a quadratic representation of what that top edge is? Then it's even better than a trapezoid. And so he figured out the area of that partition and then added infinitely many of them up and named it after himself, the Simpson rule. It's also a recipe.
I guess some quadratic shape rule doesn't sound as good as Simpson.
It doesn't. Some quadratic shape rule just doesn't sound impressive at all. Again, there's a whole lot of algebra in coming up with the Simpson's rule. I'm going to show it to you, and you say, "Whew, I'm glad Simpson did that, so I don't have to do that anymore." This is what Simpson's rule boils down to, and notice that this width of the thing, which is no longer a trapezoid, is now going to be b minus a over 3n, not 2n, like the trapezoidal rule. And you still find f of x sub 0, f of x sub 1, and so on and so on and so on, but they have the coefficients 1, and then 4, 2, 4, 2, 4, 2, until back to 1 on the very end. So what you're going to remember about Simpson's rule is you need to remember that coefficients b minus a, oops, switch back to ImageMate. You're going to remember that coefficient is b minus a over 3n, and then you're going to remember the pattern of the coefficients. First and last coefficients both have, or first and last terms both have coefficients of 1, but then the coefficients between them alternate between 4, 2, 4, 2, 4, 2, and the last one back to 1. So let's do the same problem we just did, number 10, by Simpson's rule. Still using 4 rectangles, well, 4 somethings. The width of each individual rectangle is still b minus a over n. We're still going to use a half. And we're still going to use the same x0, x1, x2, x3, x4, so I'm not going to write those down again. Simpson's rule says this definite integral equals b minus a over 3n, 2 minus 0 over 3 times 4, times 1 f of 0 plus 4 f of 1/2 plus 2 f of 1 plus 4 f of 3/2. Now we're back down to the last term whose coefficient is what? 1. All right, go for it. One thing's bugging me. Let me figure out where it is. Ah. Yeah. I got 3.39, and what's after that? 2.2. Which ought to be the better representation, trapezoidal rule or Simpson's rule? Which one should be closer to the actual value? Because using a parabola up there would give you a little bit better estimation than using a straight line for that top edge. Any questions? Anybody thinking, wait, I'm not through yet? Okay, anybody? I did 2 for a minute, right there. Is that okay, Major? Alrighty. Okay. All right. Hey, okay. Alrighty, thank you. We'll be through in just a jiffy. It's the fundamental theorem of calculus, which we use to find the antiderivative and then just plug in the lower limit and the upper limit and subtract those. So let's find the real value of this. You know, every one of those, I forgot my dx. First thing I would think, because we've got to practice, once we get a whole lot of integration methods, we've got to come up with a list that we go through in deciding which method to use. First thing I would think is that the derivative of anything that I have memorized? No, it's not. Then I would think, would U substitution work? U substitution will work if you can pick a U such that the derivative of U is accounted for there. The derivative of this U would be 2x, and differing by a constant doesn't matter, and I have the x I need right there. I think this will take the formal change of variables. I'm going to let U be x squared plus 1. Then du would be what? 2x dx. And, ooh, this is going to be ugly. What can I plug in the place of x? U. And you know what? When I take the square root of both sides.
What can you do about the informal substitution? Yeah, we can do the.
Oh, I don't have to do formal because all I'm differing by is a constant. Yeah, I don't know why all of a sudden I thought I was going to have to account for that x somehow. That x is right where it needs to be. Whew, I'm glad you saved me from that. Hey, let me make the point that I was fixing to make, and then we're going to do this the easier way. When you take the square root of both sides, what's the bells and whistles that go off in your head? Don't forget the plus or minus. How would I know if I was going to have to do it this way? And thank goodness I'm not. But if I was going to have to do it this way, how would I know whether this was going to be positive square root of u minus 1 or negative square root of u minus 1?
The limits.
On the interval from 0 to 2, you get the positive square root. All right. I don't even know why I went down that road. I'm going to say x squared plus 1 to the 1/2. And then x 2x dx is the derivative that I have to have. But is that equivalent to the line above it? Not unless I put a 1/2 out front. So make sure you have u to a power, and you have your du, and then it has to be equal to the line above it. So you need that coefficient of 1/2. All right, what's the antiderivative of ugly to the 1/2? Plus a constant. You know what? I don't even have to have plus a constant because this is a definite integral. I'm just going to say that evaluated from 0 to 2. And put a 2 in place of x. We're looking for an exact answer here, so don't pick up your calculator. What is the simplest way I can write what I have without picking up my calculator?
1/3 times 5 to the 3 halves minus 1.
All right, so you factored out the 1/3. I like that as well. You don't have to, but since it's there, why not factor out a 1/3? And in parentheses, it would leave you 5 to the 3 halves minus 1. Punch that on the calculator and see how close it is to 3.3922.
I got 3.3934.
3934, or it would round up to 3935. No?
It runs down 344.
Double check it. You have the same thing we have written right there, don't you, William?
Yes, it is 3.34. At the end is 34.
That. Which is pretty darn close to what Simpson's rule gave us, using only 4 thingies. I don't know what those thingies would be named. If we use more of those thingies, it would come closer and closer to that. What are you noticing, Dizzy?
Radix.
No. Because 3 sides are a trapezoid and the top's a quadratic. That's good. We use 4 quadratics, or we could just name them Dizzies. Because you invented a new word. All right. Last thing on this one. Our favorite thing, actually. Use numeric integration on the calculator. Math 9. And then enter the function, comma x, comma 0, comma 2. Oh, I do too. What do you get to 4 decimal places?
3.3934.
Makes sense. That means that we had this exact answer correct, because when we converted it to a decimal, we got the same decimal that TI-83 gave us. All right. Let me just explain one other thing, and we won't even take time to do another example. Trapezoidal rule, Simpson's rule, both just formulas. You memorize you memorize that coefficient. For trapezoidal rule, it's just b minus a over 2n. For Simpson's rule, it's b at minus a over 3n. And then you find your delta x, that number that you're going to count by, and you remember the coefficients. For trapezoidal rule, it's 1, 2, 2, 2, 2, 2, 2, and then back to 1. For Simpson's rule, it's 1, 4, 2, 4, 2, 4, 2 before it gets back to 1. All right, so the other thing I want to mention is the other one that I have typed and we don't have time to do. If we had tried to do that by substitution yesterday, if we hadn't talked about Simpson's rule and trapezoidal rule yet, what would you attempt on number 18? What all would occur to you? Oh! I could still see it. I don't know what your problem was. What would you have attempted on that?
The rest.
direct substitution. So maybe u is 1 plus sine squared. But real quickly, you see that's not going to work because the derivative of 1 plus sine squared would be 2 sine x for the first, and then the derivative of x is just 1, and you don't have another sine x that you can put with the dx, so that's not going to work. Do you have anything else that just occurs to you? Calculator. What if you got to find, your life depends on finding the exact answer? If your life depends on finding the exact answer, you just may die here, because neither Simpson's rule nor trapezoidal rule is going to give you the exact answer. They're going to give you very close answers, even just using 4 thingies. But if you use 100 thingies, in which case you'd probably die anyway, but if you did, then you get a very good approximation of that exact value. The thing that I was wondering if it would pop into your head. Oh, what?
Is it a double angle?
No, it's not a double angle formula. It's,
It's not cosine squared either.
I was thinking it was.
yeah, what did y'all call that? The granddaddy of, y'all call something last semester.
But it's not. It'd have to be 1 minus.
You're right. It's not even that.
That's why I checked.
Okay. If it was 1 minus sine squared, I'd plot cosine squared in its place. And then I could say the cosine, I would say the square root of cosine squared is just cosine. And if this was 1 minus sine squared, I could do that. And then I think that is something that I could integrate. Yeah, that's something that I could integrate and find an exact value. But I wanted to show you this problem to say, if u substitution doesn't work, then trapezoidal rule and Simpson's rule, only other things we have up our sleeves right now. We may get other things up our sleeves, but right now, the very best I could do with that is numerical integration by either Simpson's rule or trapezoidal rule. So you only have 4 problems in the homework, since they're going to take you a page each. On number 5 and 9, just 2 problems. Do it just like we did number 10. Use the trapezoidal rule, Simpson's rule, find the exact value, and then check it on your calculator. For number 13 and 17, you can't do those by direct substitution, so just use trapezoidal rule, Simpson's rule, and then check it on the calculator. Alrighty, thank y'all for coming on a Friday, and I will throw this on YouTube for Miss Jordan. If it doesn't snow anymore, we have 2 Fridays, 2 more Fridays.